So nice to meet you all. My name's Garth Sheldon-Coulson. I'm co-founder of Panthalassa. We're a local company here. We've been in Portland since 2019, I guess. We started in California in 2016. And I just wanted to give you the briefest introduction to what we're doing, in case you're interested maybe in joining us, or you know friends or colleagues who might be. So thanks, Dominic, for the invitation to come and talk with you. I'll keep it really short if I can, and then open it up for questions. But we're doing something that, as far as we know, no one else is doing in the world, and it's a sort of weird idea. So I'm going to try to explain it to you. What you're seeing there, incidentally, is a system called Ocean 2. It is the third prototype that we deployed. We deployed it about a year and a half ago. And what that system is doing, and what all of our systems do, is capture energy in the middle of the ocean. So these systems go to the middle of the ocean, sit there, capture energy, and we use that energy out there in the middle of the ocean to do things instead of getting it back to shore. And the big thing that we're doing first is doing lots of computing. So you can think of it like a giant, continuously extensible data center. And then later we can get the energy back to shore in the form of fuels. So that's the 30-second version, and I'll lead you through some of the ideas here. So there's the size of that system, big old systems. We make these over in Vancouver right now, and later we'll be setting up fabrication facilities in different parts of the world. This one you can see is a bit of a prototype. You know, there's some custom enhancements to the top there that we did at the last second. But the planet is basically a giant solar collector. We've got this big thing called an ocean. Ocean absorbs sun. You get convection currents that creates wind. The wind blows across the ocean, that creates waves. So the ocean is like a giant battery. And if you can build things to just go and sit out there, you get to capture that energy all the time. It can actually be quite a bit more efficient and more regular than trying to capture solar on land, where you only have it for daytime. And so this is a map of global wind speed. And what you can see is that in places like Texas, which is considered a pretty good wind resource, you've got green, and green is pretty good. But if you can get out into the middle of the ocean, there's large parts of the ocean where it's red, and it's very power dense. That wind is creating waves. So if you can just sit there with systems, you can be capturing that energy very reliably and with very high power density. And what we hypothesized at the beginning is maybe you could do it at a very, very low cost. And so that's what we set out to do. We created this system that we call a node. Took us quite a few years to get there, but it sits in the ocean like this, and it's doing three things at the same time. It's a power plant, and I'll describe how that works really briefly. And it's, in the version that we're doing now, it's a computing cluster. So all the chips are right there on the system, and it communicates by satellite. And it's a vehicle. These systems are untethered. They don't attach to the seafloor. They're out there like a vehicle. They can drive themselves around. And that means you can deploy them without touching the seafloor, don't have to dig stuff up, don't have to hammer stuff in, don't have to do it close to shore where there's conflicts with other activities. You can just send them out to the resource. And that's where the good resource is anyway. This is simulation, computational fluid dynamics. This is how they work. This is like the simplest embodiment of the system. But I'm not going to explain it all really here, but the basic idea is that it's all solid state, except for the fluids inside. So it's just the shape of the system that causes the behavior. It works like a hydroelectric dam, pumps water into itself, drives a water turbine, and then you can just take that power and power your chips or power other things like electrolyzers. But the key thing, which is different from other things in the past, is there's no structural moving parts. No hinges, flaps, hydraulics. It's just the shape, and that causes fluids to move, and that's really useful because then you could just make it out of steel. This is looking inside of one. This is looking down on the reservoir of Ocean 2. So you can see, again, I haven't really explained how it works, but water comes up and then water goes through turbines, and that's basically how it works. So like I said, we pack them full of chips, and then they drive themselves around. So this is a bird's eye view of one of them doing figure eights around those two red buoys. And they do that without moving parts as well. They drive themselves just because of their shape. So it's a new kind of energy technology. It's a new kind of vehicle. It's a new kind of computing cluster. And because it's solid state, they're really simple. You just make them out of steel cans and cones, weld them together using equipment that looks like that. And you can do that quite a bit faster than, for instance, building nuclear power plants. And steel is cheap, so that's nice. So we want to build factories like this. They won't actually look like that, but you can, like I said, just send them. And that helps you do it cheaply. So for the same price as power plant data centers on land, we can make 8 times the amount of power, which is really what people are looking for things like AI right now. And then, like I said, in the future, we retrofit the fleets and make fuels instead and get the fuels back to shore. Also, they make almost no emissions. They make no emissions, but the materials in them generate almost no emissions. It's just the steel. Obviously, compared to natural gas, it's a lot better. But even compared to things like solar and batteries, it's a lot better because those have a lot of embodied emissions, the energy required to make those things. So ours is really good on that front as well. Better than nuclear as well, better than geothermal. And so what we're doing now is we're building the next fleet. This is a series called Ocean 3. I will be putting these out starting this year. I was just up there watching one of the pieces get inserted today. It's for the Freedom.1 device. And we're actually setting up a pilot manufacturing line in this building. It's empty right now, but we're putting down all the equipment so we can start to make them really quickly. Right now, we're still making them in sort of old-fashioned way. But we make all the turbines ourselves. We make all the generators ourselves. We make all the power electronics ourselves. So if you know anyone or if you are into those kinds of things, we also have software teams. We have, obviously, mechanical engineering. We have lots of simulation, lots of different groups that are doing all kinds of different things. So if you're into any of the components of the stack, please look on our jobs board, panthalassa.com. And it comes together in systems like this. We're about, what are we now? We're about 90 people now, growing pretty quickly. And so, yeah, we love Portland. Portland's been really good to us. If you're interested in this kind of thing, please be in touch. Yeah, that's where we're going. Thank you.
What are those logos on page showed us?
Those are just where people are from on our team. Just a random sample of people on the team. There'll be lots of Blue Origin, lots of SpaceX people, Tesla, but also machine shops, kindergartens. Yeah.
And I'll bring a mic out here to folks out.
Great.
Okay. How long does a node last out in the open?
We're designing them for a 20-year life, at least the hull. We can give them coatings that lasts a good long time. The coatings are really good these days. And then the turbines, we also are designing for a 20-year life, but we bring the nodes back to shore to swap the payloads probably every 3 to 5, maybe 6 years. So we could swap the turbines at that time if we needed to, but we're trying to avoid that. It's just that one piece of rotating machinery, and you can make that last a really long time.
Hello? So who are the customers?
So the customers are big groups that need lots of compute.
So it's just like data center.
It's people who use data centers. Yeah, we'll have some big announcements about this later in the year.
How much bolting hour do they have compared, to stay on station?
Yeah, great question. So in nominal Cs, they move at about a knot or a knot and a half. So that gives them authority to, in almost all conditions, maintain station pretty well. In a big storm, we might get pushed off 10 miles, and then we have to work our way back, at least with our current designs. We're always enhancing this. So, in the future, hopefully we have really good authority. But right now it's perfectly good, and we run a lot of simulations of this. And the regions of the ocean we're in are very large, so it's not like if you get knocked off 10 miles, you're in trouble. And to be clear, we don't operate close to shore. And did I say that? Anyway, we like to be out in the middle of the ocean.
What's the average power output of the turbine or the system? Usable power.
200 to 500 kilowatts typically. Yeah, that's in the future we have plans to go up higher than that, but that's the current designs.
Just a follow-up to the last one. How does the energy density compare to, say, mechanical system?
So I know you're a wave energy guy. We have capture width ratios in the 10 to 15% range. So it's it's up there with the best 2X that have been developed. But solid state and quite a bit cheaper.
Are there risks of sabotage or collisions or theft in the middle of the ocean?
There are, yes. Those are risks that we have to mitigate. We do all of the right things to mitigate collision risks. People know where we are. We have lights, AIS, radar reflectors, all of those things. Sabotage and piracy in the regions of the ocean where we operate, there's not that many people who are there or want to be there. It's not like your average Somali pirate is going to be but it's something that we really take seriously, and we're doing a lot of things to mitigate those risks. If we think we're safer than like substations and oil tankers.
How do they tolerate exposure to debris, be that floating trash or maybe letting things out there in the ocean?
Yeah, great question. So the system doesn't have a net flow of water through it. It recirculates its water with only a tiny bit of mixing. And so there's not something that's sort of like sucking things through. And that means that on balance, things don't get ingested into the system. Also, the only inlet to the system is quite a ways down. And so, but it's not at the seafloor. So we don't take floating things because they live at the surface, and we don't take heavy things because they live at the seafloor. So you're sort of in this zone where there's not a lot of stuff to bring into the system. And then we have a net in case there is like a seal that gets really curious. Sure.
A couple more questions?
Lots of admiration for this audacious project. Another audacious project related to data centers that I've been hearing about recently is data centers in space. And with one of the ways that data centers in space has been explained to me is that space is an ideal place for data centers because energy is abundant, with solar energy being somewhere around like 30% or radiant. Cooling is not an issue, which of course cooling in the ocean is fantastic as well. And then communication via like lasers is also like something that is easily done, like the way that space data centers could be set up. Have you guys worked with or are you guys talking to companies that are trying to do space data center stuff, similar to how like NASA is training underwater to prepare for the ocean or to prepare for space as well?
Yeah, all of our big customer groups are looking at this hard. Some of them have their own programs for it. And there's a huge range of opinions on this. From our perspective, well, anyway, some of the challenges in space are much easier in our contexts. So, for example, cooling is really the big one. Like, as you probably know, space is cold, but actually it's very hard to get rid of heat in space. There's no fluid around you to conduct the heat to, so all of it has to be emitted as radiation, which means you need big radiators, black body radiators, and you need to point them in the direction opposite the sun, or at least away from the sun, because you need to be pointing your solar panels at the sun, and that gets hot. So it's actually extremely hard to do heat rejection in space. It's very easy for us to do heat rejection, and that increases their cost a lot. Of course, they have launch costs. They have a lot of vibe on launch. They've got to have a lot of radiation shielding, which is expensive and increases their weights, and their weight is very expensive because you have to launch it. So most of the people who have analyzed this from first principles have reached the conclusion that it's going to be quite a bit more expensive to do it in space than on land. We're quite a bit cheaper than on land. So at least that's my pitch, and it's true. So
As you scale over the next few years, do you have like an approximation to what a fleet size would look like?
We want to be at the many, many gigawatt scale. So many, many, many thousands of units.
Yeah, how many do you have there right now, and will you see it in 5 and 10 years? And do you have any competition? Is anyone kind of looking at you and say, hey, we'd like to steal this?
Yeah. We think about our competition as like natural gas and nuclear and those kinds of things. We don't know of any companies that are doing the play that we're doing for the middle of the ocean. We have a lot of patents on a lot of pieces of it, so it'd be hard at this point to try to compete with us for that reason. But in the future, we may. Like maybe the Chinese will decide to dread copy us or something like that. The Ocean 3 series will be the next series that we put out. So we don't have many systems out there right now. We did Ocean 2, we did Ocean 1 before that, and Wavehopper. So some of those systems I showed you that were prototype systems. So this Ocean 3 series will be our first commercial pilot fleet. And once that is demonstrated, that'll be 3 to 5 systems probably. Then we'll start to mass produce what are called Ocean 4 systems. That'll be our true commercial system in about a year and a half.
So how many are floating on the ocean today?
Today, 0. Oh, but yeah.
Okay, one more question. Anyone who's got the most burning question? Who wants the last one? Okay.
How do you, and when we navigating international waters, like which country gets to benefit from, and if conflicts arise between those countries, like if your node ended up in certain waters and that they claim that they should get the gigawatts the US pretty much, and the US is trying to say no to that.
Yeah, you can imagine some interesting geopolitical conflicts. So I don't know if you guys know the history of like the law of the sea, but the reason it exists is because there was a time when the colonial powers actually tried to exert sovereignty over the ocean. And like, I forget if it was Portugal or whatever, Spain tried to like say, oh, the ocean is ours. And basically the international community came to the view that like, no, it should be everyone's. So the law of the sea says that everyone has a right to be there in the international waters resources. And so we are in that sense, just like a sailboat or something else that's capturing the environmental energy. But we have a choice over time of whether we want to bring the systems under the sovereignty of a country by like flagging them or not. Most autonomous systems today are not vessels, not flags. They're just autonomous systems. And so we may also do that route over time. But what it basically means is that the systems are owned by a company like us that's a U.S. company, but they're not operating in the sovereign jurisdiction of any country.
Okay. Thank you. Round of applause.